You might think we know the sun. Hot, bright, 93 million miles away. Burning for billions of years, stable and predictable. Almost boring. But that's no longer the case. Right now, in 2025, the sun is at its most active point in over a decade. And it's doing things that challenge everything scientists thought they understood. Flares aren't just erupting, they're colliding. Magnetic fields are twisting in ways our models didn't predict. And one tiny spacecraft, flying straight into the chaos, caught it all in real time. The sun is alive, unpredictable, and right. Now, it's showing us a side we've never seen before. We're in the middle of solar maximum. The peak of the sun's 11-year cycle. It's when the magnetic field tangles, sunspots appear, and the surface grows restless. Normally, each cycle is predictable. Poles flip, the sun breathes in and out. But solar cycle 25 surprised everyone. Predictions said it would be weak, quiet, uneventful. Instead, we're seeing more sunspots than expected, forming clusters, erupting in chain reactions. These aren't just dark spots, they're pressure points, storing enormous magnetic energy. When that pressure releases, it sends flares and coronal mass ejections flying into space, sometimes straight toward Earth. And when it does, the effects are real. In May 2024, storms from active region AR3664 disrupted GPS in Canada and Scandinavia, caused radio blackouts critical for airlines, and reminded scientists that even a seemingly calm sun can produce chaos. Most people didn't notice, unless a flight was cancelled or a power grid flickered. It quietly passed overhead. But for scientists, this was a wake-up call. The sun doesn't wait for us to be ready. The Parker Solar Probe changed everything. Instead of observing from afar, it flies directly into the sun's outer atmosphere, the corona. Reaching speeds up to 690,000 kilometers per hour. Its carbon composite shield survives temperatures above 1300 degrees Celsius, keeping delicate instruments inside safe. And it's catching events no one expected. During a recent flyby, Parker encountered not one, but two coronal mass ejections merging into a single chaotic storm. Magnetic loops twisted, part of the corona folded in on itself, and Parker flew straight through it. The instruments recorded a spike in particle density, a drop in magnetic pressure, and a brief burst of radio signals unlike anything seen before. Scientists are calling it a compound CMEA phenomenon, theorized, but never observed up close until now. The implications for Earth are significant. One CME is dangerous enough. Two merging together can overwhelm satellites, disrupt GPS, interfere with radio communications, and even threaten power grids. Historical events remind us what's at stake. In 1989, a geomagnetic storm knocked out power for 6 million people in Quebec. In 2003, the Halloween storms damaged transformers in Sweden and South Africa. And the Carrington event of 1859, telegraph wires caught fire. Auroras reached the Caribbean. Imagine that today. With our reliance on satellites and digital infrastructure, Parker's observations aren't just fascinating, they're a warning. But Parker isn't alone. The solar orbiter provides a distant, pole-focused perspective, capturing the sun's polar regions in unprecedented detail. Early 2025 images of the South Pole revealed chaotic magnetic strands, fast-moving plasma loops, and independent rotations. Models predicted smooth, predictable behavior, but reality was turbulent. This challenges our understanding of the sun's magnetic cycle, showing us that the poles don't follow neat rules. Future missions promise even more insights. MUSE, set to launch no earlier than 2027, will create high-resolution 3D scans of the solar atmosphere, tracking small-scale energy bursts invisible from previous observations. These tiny events, occurring in quiet regions of the sun, could explain why the corona is over 1 million degrees Celsius, while the surface remains under 60 degrees Celsius. PUNCH, a constellation of small satellites, visualizes the solar wind itself, the constant stream of particles shaping our entire solar system. Each mission plays a unique role, filling gaps and giving us a complete multi-angle understanding of the sun's behavior. The more we observe, the more complex the sun becomes. Its magnetic fields don't follow tidy loops, solar wind doesn't flow evenly, and flares can erupt suddenly without warning. For decades, the sun was treated as a solved problem, predictable and safe. But real-time data reveals turbulence, irregularity, and energy releases that challenge our old models. The sun is living, dynamic, and far less under control than we imagined. And then there's the question of observations of sun-like stars reveal eruptions hundreds or thousands of times stronger than anything recorded from our sun. Some scientists believe our star might be capable of similar events under the right conditions: strong magnetic fields, high sunspot activity, and chain reactions like the ones Parker just observed. Historical clues from ice cores and tree rings hint at past radiation spikes, possibly caused by extremely powerful solar events. We can't say for sure. We've only been monitoring the sun in detail for a few decades. Cosmic time is much longer. What we do know is that we're finally inside the sun's environment. Parker flies through eruptions. Solar Orbiter observes the poles. MUSE will capture 3D energy flows and punch maps the solar wind. We're no longer waiting for signals to reach Earth. We're seeing storms as they form, tracking their progression, and learning to predict their potential impact. Real-time observation allows scientists to catch escalations that would have gone unnoticed in the past, building models based on actual measurements rather than assumptions. The consequences are more than theoretical. Every flare, CME, and magnetic fold can disrupt satellites, GPS, radio, and power grids. Recent storms have even caused low-latitude auroras in unexpected places like New Mexico, Rome, and the Mediterranean. Beautiful to the eye, dangerous in reality. The sun is revealing both its destructive power and its delicate complexity, reminding us that beauty and danger often come hand in hand. We've entered a new era of solar science. The sun is no longer a distant, predictable star. It's a dynamic, sometimes violent force that we can now study from within. Every observation brings surprises, every flare carries lessons, and every storm, whether minor or extreme, tells us more about the star that created our world. We thought we knew the sun, but the closer we look, the less predictable it becomes. Magnetic fields fold, flares merge, solar wind surges, and auroras dance in unexpected places. Parker, Solar Orbiter, MUSE, and Punch are giving us a full picture for the first time, showing that the sun's story is far from over. For centuries, humanity observed from afar, waiting and guessing. Now we're inside its storms, listening, learning, and preparing. And that might be the most important discovery of all. The sun isn't just light in the sky. It's a living star, speaking in energy, plasma, and magnetic fields, and we're finally beginning to understand its language. Flares aren't just erupting, they're colliding. Magnetic fields are twisting in ways our models didn't predict. And one tiny spacecraft, flying straight into the chaos, caught it all in real time. The sun is alive, unpredictable, and right now, it's showing us a side we've never seen before. And what Parker saw could change everything we thought we knew about our closest star. We're in the middle of solar maximum, the peak of the sun's 11-year cycle. Magnetic poles are tangled, sunspots are appearing, and the surface grows. Restless normally, each cycle is predictable. Poles flip, the sun breathes in and out. But solar cycle 25 surprised everyone. Predictions said it would be weak, quiet, uneventful. Instead, we're seeing more sunspots than expected, forming clusters, erupting one after the other in chain reactions. These aren't just dark spots, they're pressure points, storing enormous magnetic energy. And when that energy finally releases, it doesn't just explode quietly in space. Sometimes it aims straight at Earth, and that's when things get serious. In May 24, storms from active region AR3664 disrupted GPS in Canada and Scandinavia, and triggered radio blackouts critical for airlines. Most people didn't even notice. But for scientists, it was a stark reminder. The sun doesn't wait for us to be ready. And this year, the sun is only getting louder. The energy, The flares, the storms they're building, merging, escalating. If we think we've seen it all, we haven't. Enter the Parker Solar Probe. Instead of observing from a safe distance, it dives straight into the sun's corona, reaching speeds up to 690,000 kilometers per hour. Its carbon composite shield survives temperatures over 1300 degrees Celsius, keeping delicate instruments safe inside. And what it found was unprecedented. 2 coronal mass ejections didn't just erupt, they collided and merged mid-flight, creating a compound, CME. Magnetic loops twisted, part of the corona folded in on itself, and Parker flew straight through it. The instruments recorded spikes in particle density, magnetic collapse, and radio signals unlike anything previously seen. Scientists are calling it a compound CMEA, storm theorized but never measured up close. And this tiny encounter could rewrite what we know about solar storms. The stakes are real. 1 CME can disrupt satellites, GPS, and power grids. 2 merging together. Catastrophic potential. Historical events remind us: 1989, Quebec blackout; 2003, Halloween storms; 1859, Carrington event, telegraph wires catching; fire auroras in the Caribbean. Now imagine that today, with our global dependence on digital systems, Parker's observation isn't just fascinating, it's a warning that the sun can surprise us in ways we're only beginning to measure. Parker isn't alone. The Solar Orbiter gives us a pole-to-pole view, capturing the sun's magnetic poles in detail no one has ever seen. Early 2025 images of the South Pole revealed twisted magnetic strands and fast-moving plasma loops rotating independently of the surface. Models predicted calm, predictable fields, but reality was turbulence. Layers moving out of sync, chaos layered upon chaos. The sun's magnetic cycle isn't as neat as we thought. What drives it? We don't fully know yet. Future missions promise even more insight. MUSE, launching no earlier than 2027, will create 3D scans of the solar atmosphere, tracking tiny bursts of energy that could explain why the corona is over 1 million degrees, while the surface is just under 60 degrees Celsius. Punch, a constellation of small satellites, visualizes the solar wind itself, the constant particle flow shaping the entire solar system. Parker gives the close-up. Orbiter provides context. MUSE will reveal the hidden mechanics. Punch tracks the flow. Together, they're creating a full picture of the sun's behavior, one we've never had before. And the sun is proving more unpredictable than anyone imagined. Its magnetic fields don't follow neat loops. Flares erupt without warning. Solar wind surges in chaotic bursts. The sun isn't a stable, reliable machine, it's a restless, tangled system of energy, constantly snapping and reconnecting. And what we're seeing now during solar maximum might be just a hint of what it's truly capable of. Then there's the possibility of flares. Stars like ours have been seen erupting with energy hundreds or even thousands of times greater than anything our sun has produced in recorded history. Could our sun do the same? Historical evidence from ice cores and tree rings shows mysterious radiation spikes, possibly from extreme solar events we've only been observing in detail. For a few decades, superflares could be rare, happening once every few thousand years, but there's no way to dismiss the possibility. And what Parker witnessed, with merging CMEs and twisted magnetic fields, might be an early warning of the kind of instability that could trigger something far more powerful. We're no longer passive observers. Parker flies through eruptions. Solar Orbiter watches the poles. MUSE will track small energy releases in 3D punch maps the solar wind. For the first time, we're inside the sun's environment, tracking storms as they form. Flares that once appeared small can escalate mid-flight. Chains of eruptions. Merging magnetic fields, they're no longer invisible until they hit Earth. This is real-time solar science, and it's rewriting the rules. The consequences are both awe-inspiring and dangerous. Recent storms have triggered auroras as far south as New Mexico, Rome, and the Mediterranean. Beautiful, yes, but Each aurora is paired with surges of energy capable of affecting satellites, navigation, and power grids. The sun's beauty is inseparable from its risk. And as activity ramps up, both are becoming more frequent. Scientists are finally getting the data they need to predict, prepare, and protect. But infrastructure, old satellites, and terrestrial systems weren't built for this new level of solar chaos. We've entered a new era. The sun is no longer just a distant, predictable star. It's dynamic, volatile, and alive. Every flare, CME, and magnetic fold teaches us something new. Parker, Solar Orbiter, Muse, and Punch together give us a complete picture for the first time, revealing a sun far more powerful and unpredictable than anyone imagined. For centuries, humanity observed from afar, waiting, guessing. Now, we're inside its storms, listening, learning, and preparing. We thought we knew the sun, but the closer we look, the less predictable it becomes. Magnetic fields fold, flares merge, solar wind surges, auroras appear in unusual places. The sun is speaking in energy, plasma, and magnetic fields, and, finally, for the first time, we're beginning to understand its language. And the question remains, if the sun is capable of this now, what else has it been hiding all along? You think you know the sun, bright hot, 93 million miles away, burning for billions of years, predictable, almost boring. But that's about to change. Right now, in 2025, the sun is at its most active point in over a decade. Flares aren't just erupting, they're colliding. Magnetic fields are twisting in ways our models didn't predict. And one tiny spacecraft, flying straight into the chaos, caught it all in real time. What Parker saw could change everything we thought we knew about our closest star. And the real question is, are we ready for what comes next? We're in the middle of solar maximum, the peak of the sun's 11-year cycle. Magnetic poles are tangled, sunspots appear, and the surface is restless. Usually, cycles are predictable. Poles flip, the sun breathes in and out. But solar cycle 25 is different. Predicted to be weak, it's far from quiet. Sunspots are appearing in clusters, erupting one after another in a chain reaction. These dark spots are pressure points storing enormous energy. And when that energy releases, it can head straight for Earth. Could we really handle it if it did? In May 2024, storms from active region AR3664 disrupted GPS in Canada and Scandinavia, triggered radio blackouts for airlines, and reminded us just how fragile our tech is. Most people didn't notice, but scientists did. And now, with activity ramping up, the sun isn't just sending little nudges, it's roaring. If this is just the beginning, what's coming next could be unprecedented. Then there's Parker. Unlike previous missions that stay at a safe distance, Parker dives into the sun's corona, reaching speeds of 690,000 kilometers per hour. Its carbon composite shield survives temperatures above 1300 degrees Celsius, keeping delicate instruments safe inside. And recently, Parker encountered something extraordinary. Not one, but two coronal mass ejections merging mid-flight. Magnetic loops twisted. Part of the corona folded in on itself, and Parker flew straight through it. The instruments recorded spikes, collapses, and radio signals unlike anything previously seen. Scientists call it a compound CME, and this tiny encounter might rewrite everything we know about solar storms. The stakes are real. 1. CME can disrupt satellites, GPS, and power grids. 2. Merging together, catastrophic potential. History reminds us. 1989, Quebec blackout. 2003, Halloween storms. 1859, the Carrington Ventolograph wires caught fire, auroras visible in the Caribbean. Now imagine that today, with our digital dependence. Parker's observation isn't just fascinating, it's a warning. And it raises a chilling question. Could something like this happen tomorrow, without warning? Parker isn't alone. The Solar Orbiter gives a full pole-to-pole perspective, capturing the sun's magnetic poles like never before. Early 2025 images, of the South Pole revealed twisted magnetic strands, plasma loops, moving independently of the surface. Predictions expected calm, smooth fields. Instead, it was chaos. Layers of motion stacked out of sync, turbulence where models predicted order. How exactly is the sun's magnetic cycle driven? We don't fully know yet. And the answer could be closer than we think. Looking ahead, MUSE, set to launch no earlier than 2027, will create 3D scans of the solar atmosphere, capturing tiny bursts of energy invisible until now. Punch, a constellation of small satellites, visualizes the solar wind, the constant particle flow shaping the solar system. Parker gives a close-up, Orbiter provides context, MUSE will reveal hidden mechanics, and Punch tracks the flow. Together, they're building the first complete picture of the sun's activity. And it's already proving more unpredictable than anyone imagined. Magnetic fields don't follow neat loops. Solar wind surges unexpectedly. Flares erupt without warning. The sun isn't stable, it's a restless, tangled system of energy, constantly snapping and reconnecting. And what we see now might be just the beginning. Could these merging flares be a warning of something far larger? Something we've never encountered? Then there's the concept of superflares. Stars like ours erupt with energy, hundreds, even thousands of times stronger than anything recorded from the sun. Could our sun do the same? Ice cores and tree rings hint at mysterious radiation spikes, possibly from extreme solar events. We've only monitored the sun in detail for decades. Superflares might. Solar maximum isn't just a concept in a textbook, it's happening. Magnetic fields twist, poles flip, sunspots appear, and cluster like pressure points on the sun's surface. Each sunspot stores enormous energy, like a coiled spring ready to snap. And when that energy releases, it doesn't just light up space, it sends flares, coronal mass ejections, and charged particles hurtling through the solar system. Sometimes, those eruptions aim directly at Earth. And when that happens, the consequences are immediate. Satellites fail, GPS signals vanish, power grids wobble, and radio communications go dark. May 2024 was a warning. Active region AR3664 unleashed a series of solar storms that disrupted GPS in Canada and Scandinavia, and triggered radio blackouts over the North Atlantic. Airlines scrambled, engineers worked overtime, and yet most people never noticed. The sun had flexed its muscles, and humanity had barely felt it. Now, just months later, activity is surging. Predictions for Solar Cycle 25 were too optimistic, quiet, mostly uneventful. Reality is proving far more chaotic. Sunspots aren't evenly spread, they cluster, erupting one after the other, almost like dominoes falling. Every eruption increases the likelihood of something larger, more dangerous, and completely unexpected. Enter the Parker Solar Probe. Unlike past missions that stayed far from danger, Parker dives straight into the sun's outer atmosphere, skimming just 7.3 million kilometers above the surface. That's close enough to literally fly through solar eruptions. Speeds reach up to 690,000 kilometers per hour. Temperatures on the heat shield top 1300 degrees Celsius, yet inside, instruments remain just above room temperature. And what Parker recently witnessed was unprecedented. Two coronal mass ejections collided, merged, and created a magnetic structure that twisted and compressed the sun's corona in ways never observed before. Scientists call it a compound CME, and the implications are huge. This isn't just science fiction. One CME can damage satellites, disrupt communications, and interfere with power grids. 2. Merging catastrophic potential. History reminds us. 1989, the Quebec blackout. 2003, the Halloween storms. 1859, the Carrington event, which fried telegraphs and created auroras visible in the Caribbean. Imagine one of those events today, with the digital world we rely on for banking, transportation, and communication. Parker's observation isn't just fascinating, it's a warning. And the terrifying part: we have no idea how often these compound CMEs occur. because we've only had the tools to see them recently. Could the next one hit us tomorrow? Parker isn't the only observer. The Solar Orbiter, a joint mission by NASA and ESA, gives us a full pole-to-pole view. Early 2025 images of the Sun's south pole revealed twisted magnetic strands and fast-moving loops that rotate independently from the surface below. Models predicted calm, predictable behavior, but what they found was chaos layered on chaos. A turbulence that challenges decades of solar theory. What's driving the Sun's magnetic cycle? How do these polar fields control activity? We don't fully know yet. And these questions matter because the answers could determine how we predict the Sun's next move. Future missions promise even deeper insight. MUSE, launching no earlier than 2027, will create 3D scans of the solar atmosphere, capturing tiny bursts of energy invisible until now. These bursts, called magnetic reconvections, release enormous amounts of energy in seconds and may explain why the corona is over 1 million degrees, while the surface barely reaches 60 degrees Celsius. Punch a constellation of small satellites. The solar wind, the continuous flow of charged particles shaping the solar system. Parker gives a close-up. Orbiter provides context. MUSE reveals mechanics. Punch maps the flow. Together, they create a complete picture of the Sun in motion, one we've never had before, and what we're seeing is startling. The Sun isn't a calm, predictable star. Magnetic fields twist and collapse, solar wind surges unexpectedly, flares erupt without warning. The Sun is a restless, tangled system of energy. What Parker observed, the merging CMEs, the magnetic folding, might be just the beginning of something larger, something the models don't yet account for. Could these compound events be precursors to a superflare? Superflares aren't science fiction. Observations of other Sun-like stars show eruptions hundreds or thousands of times stronger than anything we've recorded on Earth. Could our Sun do the same? Historical records, ice cores, and tree rings hint at mysterious spikes in radiation over the centuries. Could these have been ancient solar superflares? We don't know. We've only been observing the Sun in detail for a few decades. The possibility exists, and Parker's data may help us understand whether the Sun has the potential to produce these extreme events. We are no longer passive observers. Parker dives through storms. Solar Orbiter captures the poles. MUSE will track microbursts of energy. Punch maps the solar wind. Real-time observations mean we can see eruptions as they happen, not minutes or hours later. That's critical. Flares that seem small at first can escalate mid-flight. Chains of eruptions can merge, and compound CMEs can form all without warning. This is live solar science, changing everything we thought we knew. The consequences are breathtaking and dangerous. Auroras appear far from their usual latitudes: New Mexico, Rome, the Mediterranean. Stunning, yes, but behind the beauty lies risk. Surges of energy can disrupt satellites, navigation systems, and power grids. Solar activity is increasing, and both the lights in the sky and the hidden dangers are becoming more frequent. The science isn't just fascinating, it's urgent. Are we ready for what comes next? We've entered a new era. The Sun is alive, chaotic, and unpredictable. Magnetic fields fold. Flares merge. Solar wind surges. Every CME teaches us something new. Parker, Solar Orbiter, MUSE, and Punch together give us the first complete picture of our Sun. For centuries, humanity observed from afar. Now we're inside the storms, listening, learning, preparing, but we thought we knew the Sun. But the closer we look, the less predictable it becomes. Magnetic fields fold, flares merge, solar wind surges, auroras appear in unusual places. The Sun speaks in energy, plasma, and magnetic fields, and for the first time, we're beginning to understand its language. But the question remains, if the Sun is capable of this now, what else has it been hiding? And when or if its next move comes, will we be ready? We often take the Sun for granted. It's always been there, rising every day, warming our planet, powering life. But that calm, familiar presence is deceptive. Underneath its bright surface, a storm is raging, a storm that has been billions of years in the making, but one that we're only now able to watch up close. Every sunspot, every flare, every coronal mass ejection tells a story of immense power, of energy released in ways we cannot yet fully predict. Think of solar cycle 25. It began in late 2019 with modest expectations. Scientists predicted a quiet period, fewer sunspots, less activity than the previous cycle. Instead, the sun surprised everyone. Sunspots proliferated, forming clusters that erupted repeatedly. Magnetic fields twisted and tangled. Each eruption sent charged particles and radiation into space, some aimed toward Earth. And these weren't isolated events. They were chains, domino-like sequences that could amplify and merge, creating storms unlike anything observed in decades. In May 2024, active region AR3664 demonstrated the sun's disruptive potential. GPS signals in northern latitudes became unreliable, airlines faced radio blackouts, engineers scrambled to reroute communication and navigation. On the surface, life went on, most people didn't notice. But behind the scenes, scientists were watching, understanding that the sun was far from predictable. By mid-2025, the activity reached a peak, and multiple space agencies began issuing frequent alerts. While amateur astronomers reported auroras in unusual latitudes from Arizona to France, even across parts of the Mediterranean. Enter the Parker Solar Probe, humanity's first craft to dive directly into the sun's corona. Conventional spacecraft avoid danger, but Parker doesn't. Reaching speeds of 690,000 kilometers per hour, it endures heat exceeding 1300 degrees Celsius with a carbon composite shield protecting sensitive instruments inside. And during its recent flybys, Parker observed something unprecedented: 2 coronal mass ejections colliding mid-flight, merging into a structure that twisted and compressed the sun's corona. Magnetic loops folded over themselves, particle densities spiked, radio signals erupted. Scientists call this a compound CME, and it could change how we understand solar storms, their formation, and their potential effects on Earth. One CME alone can disrupt satellites, overload power grids, and interfere with navigation. To merging, catastrophic potential, history provides sobering reminders. The 1989 Quebec blackout, the 2003 Halloween storms, the 1859 Carrington event. In today's interconnected world, there's a part of us that thinks we've already figured out the sun. We learn about it early on, hot, bright, 93 million miles away, been burning for billions of years. It feels stable, predictable, almost boring. But that's not really true anymore. Right now, the sun is hitting the most active point it's been in over a decade. And it's not just sending off flares and storms. It's doing things we didn't think it could do. One NASA probe flew right through the chaos and saw something strange, something we've never caught in action before. This wasn't just another solar flare. Multiple eruptions slammed into each other, fused together, and created a magnetic ripple so powerful it bent part of the sun's outer layer. Scientists are still trying to figure out what that means. And here's the part that's bothering a lot of them. This kind of behavior doesn't really fit the models. It's not supposed to happen like this. So now we're left with a question we haven't had to ask in a long time. Do we actually understand how our own star works? Or has it been hiding something? In plain sight, you probably haven't noticed anything unusual when you look up during the day. The sun still rises and sets like clockwork. No changes to the color, no warning signs in the sky. But behind that calm appearance, something big is happening. We're right in the middle of something called solar maximum. It's the most active phase in the sun's natural cycle, a period when the magnetic field gets tangled, twisted, and unstable. And when that happens, the surface becomes restless. Sunspots form, flares erupt, and huge clouds of charged particles get hurled into space at high speeds. This cycle has been going on for billions of years. It repeats roughly every 11 years, like the sun breathing in and out. One cycle ends, the next begins. And each time, the magnetic poles flip. North becomes south, and vice versa. It's not instant, and it's not clean. The flip takes time, and during that period, the sun becomes chaotic. Right now, in 2025, we're at the peak of solar cycle 25. That means the magnetic field is tangled up more than usual. The number of sunspots is going up. And those sunspots, they're not just dark patches. They're active regions that store enormous amounts of magnetic energy. Think of them like pressure points on the surface. When the pressure builds too much, something snaps and you get an explosion. A solar flare, or worse, a coronal mass ejection. Solar cycle 25 wasn't expected to be this strong. When it started in late 2019, predictions said it would be weaker than the last one. Quiet, mostly uneventful. But that's not what's happening. Over the past few months, scientists have been seeing more sunspots than they expected, and they're not evenly spread out either. Some of them are forming in clusters, erupting one after the other, almost like a chain reaction. That's where things start to get interesting, because every time one of those flares or coronal mass ejection bursts off the sun, it sends radiation and charged particles out into space. Most of the time, that energy just keeps going. But if the direction is right, if it's aimed at Earth, it can mess with satellites, interrupt radio signals, and even damage power grids. And this isn't theoretical. We've already seen real effects. From this cycle, in May, a series of powerful solar storms from active region, AR3664, caused significant GPS disruptions in high-latitude regions, like parts of Canada and Scandinavia, due to ionospheric disturbances. These storms also triggered strong radio blackouts, impacting shortwave communications critical for airlines over the North Atlantic. While no injuries occurred, these disruptions required communication workarounds and raised serious questions about our preparedness for stronger solar events. Now, in mid-2025, we're at the height of the storm. The peak of solar maximum isn't a single day. It's more like a messy season that lasts a year or two. That's why this summer is getting so much attention. Multiple agencies, including NASA, NOAA, and ESA, have started issuing more frequent space weather alerts. And amateur astronomers, they're spotting auroras in places where they're rare, such as Arizona, France, and even as far south as parts of the Mediterranean region. But even with all this happening, the general public barely hears about it. Unless it causes an outage or cancels a flight, space weather doesn't make the news. It's quiet, invisible, easy to ignore. And that's part of the problem, because while everything seems fine on the surface, the sun is pushing out more energy, more flares, and more magnetically charged debris than it has in over a decade. It's like living next to a volcano that's suddenly more active. And most people don't even know it's rumbling. This isn't fin-mongering, this is physics. And now that the sun is fully awake, scientists are watching closely, because if anything unusual is going to happen, something that challenges the models, it's going to happen. Now, before we continue, if you've ever landed in a new country and immediately gone into panic mode because there's no Wi-Fi, you'll know how frustrating that feels. Either you're stuck paying insane roaming fees, wasting time hunting for a local SIM, or taking your chances with someone selling one outside the airport. I've been there, and it's the worst way to start a trip. That's why I use Sai. It's an ES app, which means no physical SIM card, no switching tiny trays in your phone, and no standing in line just to get connected. You install it once on your phone, pick a plan for wherever you're going. They've got coverage in over 200 destinations, and the second your plane lands, you're online. It even has built-in privacy tools that block ads, help you save data, and keep your browsing secure. It's genuinely that simple. Open the app, choose your destination, and use code FEXEL or scan the QR code on screen, and you'll instantly get 15% off your plan, making it easier to stay connected without dealing with extra costs when you return home. If we had tried to do this 20 years ago, it wouldn't have worked. The heat, the radiation, the distance, it would have melted the instruments before they even got close. But today, we've built something that can survive there. It's called the Parker Solar Probe, And it's not just watching the sun from a distance. It's flying right through its outer atmosphere. That alone is wild. Most space missions keep their distance from anything dangerous. Not Parker. It's the first spacecraft designed to dive directly into the corona, that faint outer layer of the sun that we usually only see during a total eclipse, reaching speeds of up to 690,000 km/h. To swiftly navigate this extreme environment, to survive that kind of heat, the probe is equipped with a special carbon composite heat shield that can withstand temperatures over 1,300 degrees C while keeping the instruments inside just above room temperature. Since its launch in 2018, Parker has been getting closer and closer with every orbit. By late 2024, it reached a point where it was skimming just 7.3 million kilometers above the surface. That sounds like a lot until you remember the sun is massive. Over 1 million Earths could fit inside it. At that altitude, Parker was literally flying through solar eruptions as they were happening. And then something strange happened during one of its most recent flybys. Parker passed through an active region where multiple CMEs had just erupted. Normally, these coronal mass ejections burst outward like separate explosions, independent events. But this time, something was different. As Parker approached, it picked up signs of an ongoing collision, not just between plasma clouds, but between their magnetic fields. One CME caught up with another, and the two started merging. That alone is unusual. What's weirder is what came next. Instead of just combining into a larger storm, the merged structure began to compress and warp the surrounding magnetic field in a way that hadn't been modeled before. The magnetic loops above the sun's surface, normally smooth and arched, began to twist downward like tangled rope. One part of the corona folded in on itself. It was like watching waves crash together, but made of superheated gas and magnetism. Parker flew right through it. The instruments on board recorded a sudden spike in particle density, a drop in local magnetic pressure, and a brief burst of radio signals that didn't match any known signature. For a few minutes, the data looked like static until it didn't. When scientists decoded it, they realized Parker had flown through a high-energy shock front created not by one flare, but by the fusion of two. It's being called a compound CME, and while these kinds of events have been theorized, we've never had direct close-up measurements from inside one until now. And it raises questions that go beyond just solar physics. Because when these things happen, they don't stay in the corona. They shoot out into the solar system, carrying magnetic structures that interact with everything they touch. Satellites, astronauts, Earth's magnetic field. So now scientists are going back over years of data trying to figure out how many times something like this might have happened without us knowing. Did we miss earlier compound CMEs just because we weren't close enough? Did past blackouts or anomalies line up with events like this? The answers aren't all in yet. But this one encounter, just a few minutes of data from a tiny probe buried in solar plasma, could change how we understand the way energy moves through space. Not just in our system, but in other stars too. And it's all because Parker went where nothing else ever dared to go. When the sun fires off Acme, it launches billions of tons of charged particles across space. If that cloud hits Earth, it slams into our planet's magnetic field at incredible speed.